Okay, what we're going to look at now is the fifth reaction, which is called the double displacement reaction. All right, for the double displacement reaction, what we said about this particular reaction is that this is a reaction that is typically seen at a dance. Now, remember, I told you that the dance that can really get a party started when we talked about it in class was known as the do-si-do. And if you remember the do-si-do and the way it works is basically it is two people and they interlink their arms. So they kind of put their arms together and they link them together. And then there's another couple that also has their arms that are kind of interlinked as well. And what happens is the two different couples kind of skip around the dance floor. And then what will eventually happen is they will simply switch partners. And then they'll continue to simply kind of skip around the dance floor a little bit. Well, that dance is analogous to this double displacement reaction. If you look at it closely, what you'll notice is that we've got right here our couple of this metal attached to A, which is a non-metal. We got a different metal attached to B, which is going to be a non-metal as well. So really what we have here is we got two different ionic compounds. And basically what's going to happen is this metal is going to simply switch partners and go off with the non-metal. And this metal too is going to switch partners and go off with this non-metal right here. And if you look at it, you can now see over here, I've got metal 2 now being associated with A, and metal 1 is now associated with that non-metal B. So they switch partners and we produced a new compound. So nothing more than a do-si-do. Now, one of the things I'll point out right now is that when it comes to our double displacement reactions, the reactants are going to be aqueous. So all the problems that I'll be giving you, the reactants will always be aqueous. So remember, these are ionic compounds that are the reactants here. So keep in mind, they're going to always be aqueous. Now, the products are a different story, and we'll talk about the products. The next thing we need to talk about is when it comes to a double displacement reaction, in order for there to be a reaction that actually takes place, you'll notice that in the notes, it says that you have to, as a product, have a precipitate be produced and or you have to have water being produced. So we got to get a precipitate and or water, which means that, let's go over this really quick and make sure everybody's clear. When it comes to a precipitate, don't forget that that simply means that if I mix two things that are liquids or in the aqueous state, and all of a sudden I get a solid on the product side, then that solid is referred to as a precipitate. So that is our precipitate. So either a precipitate or water being produced. Now we're going to see there are two types of double displacement reactions. There's a double displacement acid-base reaction, and if you look at it, it says, hey, this sort of reaction is going to produce that water. And there's also a double displacement precipitation reaction, where this one's going to end up producing a precipitate. So the first one to look at is going to be a double displacement acid-base reaction. And the first thing we need to do is just kind of define what is an acid. But you have to remember, we've already talked about an acid. You should know that an acid in this case is really going to be made up of some hydrogen cation attached to some anion. And remember, we said it was going to look like HX, and then we just had AQ right here because it's dissolved in water. And once again, it doesn't make a difference what that X happens to be as an anion. If I see it start off with a hydrogen and it's aqueous, it's going to be an acid. So HCl aqueous, HNO3 aqueous, those would be all acids. What's new in this case is going to be our base. And a base, look at the base definition, it says it's going to be some anion hydroxide that is attached to some cation in this case. So if we look at a base, really what we're going to have is we're going to have some cation, which is going to be a metal, attached to a hydroxide. And then it's also saying that it is dissolved in water. So once again, I don't care what metal happens to sit here. If there's a hydroxide as an anion and it's aqueous, then it is going to be classified as a base. So that metal could be sodium hydroxide aqueous, barium hydroxide aqueous. Doesn't make a difference. I see a metal hydroxide aqueous and I'm done here. Now, let's watch what's going to happen. I told you an acid. Oh, hold on one second. An acid, when it reacts with a base. If you remember, I said this sort of reaction is going to end up producing water. And if we look at it closely, it will make sense. Because we've got HX aqueous that we use as a generic acid. We had our metal hydroxide that we used as our generic base. And then what we said in this case is that the H is going to do the do-si-do and switch partners, and it's going to go off with hydroxide. The metal is going to go off with, in this case, the X. So when I write the actual products, remember, metals always come first. So here goes my metal, and here goes now it paired up with X. And then we're also going to end up getting, in this case, H plus with OH minus. And if you remember, we said H plus and OH minus is really just HOH. And if you remember from the earlier notes, when we talked about single displacement reactions, we said that this is nothing more by convention of being just H2O. So we're really producing H2O down here, and that's just going to be our liquid. So if you look at it, because every acid is always starting off with an H plus, and every base always has a hydroxide, these two will always meet to produce the water that's going to be produced for the reaction. Now, one of the things that we say in chemistry is we like to say that an acid plus a base will produce a salt plus water. And keep in mind, this salt that I referred to, a salt is the same thing as an ionic compound. They can be used interchangeably right here. Salt, ionic compound. They can be used interchangeably. So they could have said acid plus base yields ionic compound plus water, but it sounded a little bit catchier to say acid plus base yields salt plus water. And that's what we're getting here, because we do have a metal attached to a nonmetal, so clearly that's an ionic compound, or we can call it a salt. So if you look at the reaction that I have down here for the general reaction, it just simply says acid plus base yields salt plus the water. The acid and the base are always aqueous, because I told you for double displacement reactions are always going to be aqueous, the reactants. Well, by definition, an acid has to be dissolved in water. A base has to be dissolved in water, so both aqueous. As far as the salt goes, the salt, it could be aqueous or it could be solid. And I'll explain how you'll make that determination of whether it's aqueous or solid when we talk about the double displacement precipitation reaction. Then you'll understand how to choose which one it's going to be. But for right now, the ones that I'm showing you are all just aqueous here. And then I'll explain how it's possible it can be a solid. But if we look at this reaction here, hydrochloric acid, sodium hydroxide. So the hydrogen cation is going to go off with the hydroxide. Sodium will go off with the chloride. Sodium is a +1, chloride's a -1, so I get NaCl. The H plus goes off with the OH minus, so I get my water being produced. And this is actually a typo. This should not be aqueous water. That would be like water dissolving itself. It should just be a liquid sitting right there. Okay, another problem. If we take, in this case, this acid, the hydrogen cation goes off the hydroxide, calcium goes with the sulfate. Calcium is a 2+, sulfate is SO4 2-, so therefore 1 to 1, so CaSO4. For the water, we had H+ going with the OH-, so that's going to end up producing the water. And then once again, you got to go back and balance it. So let's try one more problem here. Let's say that we had something like, let's go with, we'll go phosphoric acid. And let's say that was to react with something like calcium Let's go with something else. Let's go with lithium hydroxide. Lithium hydroxide. And once again, because that's an acid and a base, by definition, they both have to be aqueous. So switching partners, hydrogen will go off with the hydroxide, lithium will go off with the phosphate. Lithium is a +1, phosphate is PO4 3 minus, so I get Li3 PO4. And I'll tell you that this one's going to be aqueous. Eventually, you'll find out how to figure out if it's aqueous or whether it's going to be a solid. So that we'll go over. Once again, we talk about the double displacement precipitation reaction. I'll explain it to you. And then we get the H plus going off with the hydroxide. So we get plus H2O. That is a liquid. Balance this thing out. I see 3 lithiums here, so let's put a 3 right here. I got 6 hydrogens on the reactant side, so I need to put a 3 right here. And it looks at this point as though it is now balanced. So that would be our balanced reaction for this acid-base reaction. So remember, just switching partners, putting everything together based upon charges. All right, on to the double displacement precipitation reactions. Now, with the double displacement precipitation reactions, what's going to happen is we're still going to see the do-si-do play out. We'll see in this case that we're not going to have an acid and we don't have a base. I don't see anything starting off with an H plus on the reactant side or a hydrogen, and I don't see any hydroxides. All I see is ionic compounds sitting on the reactant side. So what's going to happen is this hydrogen cation is going to switch places with the nitrate, and silver is going to go off with the chloride. And what's going to happen is silver, you're a +1, chloride, you're a -1. So just put them together based on charge. Over here, I got sodium. When it goes off with the nitrate, you're a +1, nitrate, you're a -1. So put them together based on charge as well. So I got the 2 compounds that were put together based on charge. And what you'll notice is that one of the compounds is going to end up being a solid and one is going to be an aqueous. And how you're going to figure out which one's going to be the solid, which we call our precipitate, because remember, you mix 2 liquids together or 2 aqueous together, you get a solid. That solid is our precipitate right here. But how are you going to figure out which one is a precipitate and which one is going to be aqueous, we'll talk about in a second. First thing I want to do is just make sure that you can switch partners. That's all you need to do right now. Next example, if I take calcium and it switches partners in this case and goes off with the anion, this cation going off with this anion, then once again, putting things together based upon charge, sodium, you are a +1, sulfate, SO4, 2 minus, you're a -1. I need 2 sodiums for every 1 sulfate. That's why I got 2 sodiums there to cancel that charge out. Calcium, you are a 2+ charge. Carbonate, you are CO3, 2 minus. So once again, just putting this calcium here with that carbonate. And once again, the charges cancel out, so they come together. And then once again, you got to balance the equation, which just shows it being balanced in this case. And then figuring out the products as far as who is the solid and who's going to be aqueous. Once again, we'll talk about that in a few minutes. But I do want to speak on this next one. This next one is interesting. If you look at it, wrong thing. When I switch partners here and have sodium go off with nitrate and ammonium go off with the chloride, and when they do switch, I'm going to end up getting now sodium, which is a +1, nitrate, NO3 -1. So I get a 1-to-1 here. Ammonium, you're a +1, chloride, you're a -1. So I get a 1-to-1 here as well. But if you look at both of the products here, both of the products happen to be aqueous. And because both of the products are aqueous, that means that we have no reaction. Because if you remember earlier in the notes, one of the things that I told you up here, it said in order for a double displacement reaction to occur, you must produce a precipitate or you have to produce water. And for this reaction right here, I don't have a precipitate because I don't have anything that's a solid. I don't have water as well, so therefore there is no reaction. Even though it looks as though something new is being produced, in actuality, there's nothing new. And we'll see this later on when we talk about what's known as a complete ionic equation, which shows us the complete picture of what's going on. And when we see the complete picture, we're going to see that there's nothing new being produced by this reaction. Just can't see it based upon this sort of balanced chemical equation. But trust me, 2 aqueous on double displacement, you're going to write down no reaction. So the question that needs to be addressed is, how do we figure out who is a solid and who is going to be, in this case, the aqueous on the product side? And the way that we're going to do this is we're going to use what is known as the solubility rules. And the solubility rules are used to predict if an ionic compound will be soluble in water. And let me explain what I mean by this. What we said in class is that if we think about something like sodium chloride, so NaCl, and if we had, in this case, a beaker of water. So here goes my beaker here. And we got some water here. If I took this sodium chloride and put it into water, then what's going to happen is the sodium is going to break into really small pieces. The pieces are so small that I cannot see it. And then we'll just simply say, hey, the sodium chloride has dissolved in water, and we'll say NaCl aqueous. And all that simply means is that sodium chloride was soluble. It dissolved in the water. But at the same time, if I take something such as silver chloride, AgCl, and if I place silver chloride into water, this silver chloride is not going to dissolve in water. It will just simply plop down to the bottom of the beaker, and I'll just get AgCl as a solid, and I'm going to say that this thing is going to be insoluble. It does not dissolve in water. So I'll just see it just plop down to the bottom of the beaker. So what's going to happen is these solubility rules, when we understand them, will tell me, even before I put the sodium chloride in water, that it's going to break apart and it's going to dissolve. It will also tell me that this thing right here, this silver chloride, even before I put it in water, it's going to say, hey, that is not going to dissolve in water. There's no need for you to even put it in there. Just trust me, I am the rules that govern whether the ionic compound will dissolve in water or not. So let's take a look at these rules really quickly, because they're not that bad. The rules go that alkali metals, and remember, alkali metals are your metals that are in the 1A family. So that 1A family, the things such as sodium, lithium, cesium, potassium, rubidium, all those elements in the 1A family, it says that these are going to be soluble salts. Remember, salt is the same thing as ionic compound, which means that if you have any ionic compound that has an alkali metal, sodium chloride, your alkali metal, you don't need to look any further. It is going to be soluble. And I don't care what is attached to that alkali metal. Lithium is an alkali metal. If I had attached to phosphate, I could care less. As soon as I see the alkali metal, I'm going to say, hey, you are soluble. You will be aqueous when dissolved in water. The same thing is true for ammonium. Ammonium is always going to be soluble in water as well, so always soluble. Now keep in mind that the alkali metals and ammonium are the only two cations that you see within the actual solubility rules. Everything else is going to be an anion that's listed here. So the rule of thumb is if you ever see an alkali metal sitting in the beginning of that compound or ammonium, you are done. Don't look any further. It will dissolve in water. Some other examples of salts that are capable of dissolving in water are things such as acetate. You can have, I don't care what acetate it happens to be, it could be iron 3 acetate. It is going to dissolve in water. So any metal attached to an acetate dissolving in water. Nitrate containing compounds, always, 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 always soluble in water. So once again, I don't care what cation is attached to it, it's going to dissolve. Now the halogens, for the most part, they are going to be soluble in water. The only exceptions for this class is actually, because we're going to get rid of this one right here, so you're not responsible for that one, is going to be silver and lead. If you see a halogen attached to a silver, it is going to be insoluble. It will not dissolve in water. If you have, wait a second, before I go any further, look back up here. Here goes a silver attached to a halogen. And if you remember, I told you it would not dissolve in water. And that's because, once again, for the most part, halogens, any other halogen, any other metal besides silver and lead too, it will dissolve in water. But silver is one of the exceptions that makes it insoluble. So it's silver and also lead too that will cause the halogens to be insoluble. What I told the class to do is just think about AP, like, the AP courses. A being silver, P being lead, and then in this case, lead too. Sulfate-containing compounds, for the most part, are soluble. However, there are three sulfates that will not dissolve in water, and that's if you have strontium, barium, and lead. And what I tell students for this one is kind of remember this, P, B, S. Here goes your lead, here goes your barium, and here goes your strontium. And luckily for us, on the periodic table, strontium is here, and barium is right underneath of it. So all you have to do is kind of, once you get strontium, realize that B is barium. You just have to memorize that P is going to be lead 2 again. That lead 2 keeps on popping up there. Now, really quickly, things that are going to be insoluble. Carbonates are insoluble. Chromates are insoluble. Phosphates are insoluble. But remember, one of the things I told you already, if you have an alkali metal or ammonium, you're done. It supersedes everything. It will always cause things to be aqueous. So what I always tell students is, once you get to the metals, if you see alkali metal or ammonium, you don't need to look any further. It's going to end up being soluble, because that, once again, is the exception to everything. They will force everybody to be soluble. But if carbonate is not hooked up to an alkali metal or ammonium, it's going to be insoluble. Same thing with chromate and phosphate. The last one is we got hydroxides and sulfides. Hydroxides and sulfides, once again, are going to be insoluble. Alkali metals and ammonium, we said that supersedes everything. And then there's a few more for the hydroxide and sulfide. You got calcium, strontium, and barium. And this one I tell students just to remember, in this case, CBS. And luckily for students, you'll find that calcium on the periodic table is right above strontium, which is right above barium. So if you remember CBS, it's just the 3 right there on the periodic table. You'll find them in the alkaline earth metals. If you look on the periodic table now, you'll see them right there. So CBS. So let's talk about how we use the solubility rules here. So let's say that I had the following reaction here. Say that I had sodium chloride, aqueous, plus I've got, in this case, something like silver nitrate, aqueous. Now remember, one of the things that I told you is that, hey, the reactants, I'm always going to set it up where the reactants are going to be soluble. But if you don't believe me, your alkali metal, sodium is, so it's got to be soluble. We said nitrate-containing compounds are always soluble, so it's always going to be soluble as well. But I'm telling you now, I will always set it up where the reactants are going to be soluble, so you don't have to use the solubility rules for them. The products you do, because if I look at it, sodium will go with nitrate, silver will go with the chloride. So what I'm going to end up getting is I'll get NaCl based upon charge, and I will also get, wait a second, wrote that wrong. I'm not going to get NaCl, I'm going to get sodium nitrate, NaNO3, and also I'll get AgCl2. Now the products, this is where we use our solubility rules. Because we're going to go in there and say, well, you're an alkali metal. I don't need to look any further. But even if I miss that, nitrate-containing compounds are also going to always be soluble as well. But I'm really going to hit that alkali metal, telling me that this thing is going to be aqueous. For the metal that's sitting here, the silver, well, you're not an alkali metal, you're not ammonium. So I'm going to have to focus my attention on the anion. And in this case, it tells me that the halogens are going to be soluble. So they are soluble except for when they're attached to silver or lead too. So because it is attached to silver, you are going to be my precipitate, and hence you're going to be my solid. Look at another example. Maybe we have something such as this reaction here. Let's go with ammonium. Ammonium carbonate reacting with calcium chloride. And once again, the reactants, I'm telling you, are always going to be soluble. And if you don't believe me, hey, your ammonium-containing compounds are always soluble. Hey, you're a halogen, chloride, you're not attached to one of your exceptions. You're also going to be soluble. But I'm telling you once again, the reactants are always going to be soluble. Here we go, going to the product side, doing the do-si-do. Ammonium, you are going off with chloride. Calcium, you're going off with carbonate. In 1 second, while this Christmas music ends, and there we go. So we'll get ammonium going off with the chloride. Ammonium is a +1, chloride's -1. And also we'll get calcium, in this case, going off with the carbonate. Calcium's a 2+, and carbonate's a 2-. Looking at the solubility rules, we said ammonium-containing compounds are always aqueous, so aqueous. In this case, if I look at it, hey, you're not an alkali metal or ammonium, so I need to look at the anion here. So I'm going to go to carbonate. And if you look at it, carbonates are going to be insoluble, except for if they're attached to an alkali metal and ammonium, and in this case, it's not. So U will be my precipitate. And then once again, the only thing I can do now is just balance it out by placing the 2 here, and I'm done. So just keep in mind that when it comes to the double displacement precipitation reactions, switch partners, and then just use the solubility rules to make the determination of who the precipitate's going to be. So even if I go back up here to these reactions here, here I can clearly see that, hey, your alkali metal, you're going to be soluble. Your carbonate, if you remember, we said carbonate-containing compounds are insoluble unless they're attached to alkali metal or ammonium. That's why that one happens to be a solid. Over here, your alkali metal, you're aqueous. Ammonium-containing compounds are always aqueous, and that's how I'm getting aqueous and aqueous here. And then one last thing just to point out, for those when I talked about single displacement reactions, so I'm going to go back just a little bit. No, not single, but I'm sorry, double displacement, acid-base reaction. Right here it says aqueous or solid. It is possible that that salt or ionic compound can be a solid, and that's really dependent upon using the solubility rules. All the ones I gave you when we looked at this double displacement acid-base reactions were set up where they were going to end up being aqueous based on the solubility rules. You're alkali metal, you're aqueous. You are sulfate in this case, and sulfate-containing compounds, if you remember, happen to be soluble. There were only, in this case, 3 exceptions, and that was using P, B, S, where P was going to be lead-2, B was going to be barium, and S was going to be strontium. And in this case, it's not one of the exceptions, and that's why it's going to be aqueous. All right, that is it for the double displacement reactions, and this is where we're going to stop then.